Thank you, Jack, and thank you, Michela. I also want to take this opportunity to thank the award committee, my nominator, and the ISA conference. Good morning, everyone. My name is Lin Gan from Tsinghua University. I want to start this talk by sharing some very good moments and pictures of my career. I got my PhD in 2016. The same year at ISA 2016, we announced this Sunway Type-Lite supercomputer, #1 in top 500 at that time, with a peak performance of more than 100 petaflops and more than 10 million cores. The same year, we invited Jack to Wuxi and had this picture. This is the first group photo I have with Jack. That's Jack and I 10 years ago. Behind us is the lake of Taihu, also the name of Sunway Taihu Lite. Then in ISA 2018, Taihu Lite became #2. So I am able to have this graphic photo with Jack on top 500 both. This is the first certificate, the first paper Jack offers to me. And also in ISA 2018, I'm very honored to give this invited talk at this conference. 2 years after graduation, invited talk at ISA conference is really a great encouragement to me for my encouragement for my future career. After that, I had the opportunity to work and talk with lots of you downstairs, and that's really helped for my career. And my latest photo with Jack was last year in Tsinghua, China, known as the Chinese Hawaii, a very beautiful city. Jack was there attending the Computer Science Development Forum for our university, for the Tsinghua University, where all the leadership of the university were there to listen advices from top experts like Jack. And I remember very clearly that Jack kept emphasizing to the leadership how important computing facilities should be for top universities, and how important high-performance computing is for top universities. This really matters and for the development of our universities and for us as the faculty members. It was also in Tsinghua last year, Jack told me everything about how to tell the difference of whiskeys. Yeah, we walked across a whiskey shop and told me a lot of knowledge about whiskeys. I know nothing of whiskey before, frankly, and I started enjoying whiskeys since then. Yeah. So in the past decade, my research focused on exploring the performance potential of different numeric applications like geophysics, climate, material, and some work on quantums based on novel architectures, including CPU, GPU, FPGA, and now some new AI chip. And also, I focus on using top universities like the Type-Lite and also the Tsinghua in China, and we try to design fine optimizations so that those applications those algorithms can fit well with those new architectures. And when we have fine optimizations, I try to design application softwares for our domain users, and also design some system or optimizing tools for the portability or for the performance improvement. And also in recent years, I also studied HPC plus AI and HPC plus quantum. So in this talk, I will briefly introduce our latest work on using FPGA, use Sunway and some AI unit for performance accelerations. So this is the architecture of Sunway supercomputers from Type-Lite to the new generation and maybe for future generations. Each CPU have a certain number of core groups. For example, Sunway Type-Lite has 4 core groups, and the new Sunway has 6 core groups. Each core group has 1 host core for controlling and 64 computing cores for doing the the computing tasks. And there are important features like all the cores, all the thread level cores can communicate with each other straightforwardly. And each core has local memory, user-controlled local memory. So those are important features that we can use. And this is the programming model. We support OpenCC plus a thread. And the picture is a thread programming model. It's like CUDA. We have separate code. We have host code, and we have computing core code that will be assigned to host core and computing cores respectively. So for these architectures, we have, in the past years, done a lot of important work. For example, we scale earthquake simulation, molecular dynamics, algorithm, and quantum simulations to more than 39 million cores of the new Sunway supercomputers, and also for the climate model, more than 10 million cores. The CAM model, we managed to port and optimize more than 700,000 codes. Most of them are in Fortran to our Sunway system. And that work was selected as the Golden Bell Finals in 2017. And after that, we are still working on it. And we designed lots of fine-grained tuning methods for those, by make the best of those important features of our processors, our architectures. For example, this is designed to use the local memory and to use the core level communications. This is an atmosphere domain. We want to scale it onto thousands of cores. And suppose this is the default element processed by one core. And in our Sunway architecture, we can adjust this kind of decomposition. For example, if the data, we want to put all the data of this element into the local memory. If we still have more local memory rooms, we can enlarge this kind of element to have more elements into one core. Or if it was the other way around, we can decompose this element into several small elements. So if such decomposition generates extra communications, those kind of communications are core-to-core communication and can be implemented, can be optimized by using the thread-level communications. The other thing is for the large-scale load balancing problems. The picture shows the default workload distribution based on Hilbert curve, and the number 0, 1, 2, 3 refer to the process that is in charge of a certain area. And if you look at these distributions, we print out all the time of all the processes onto this picture. You can see there are obviously at least three types of differences that will cause load imbalance. The first one is ocean and land difference. The second one is latitude, north and south. And the third one is day and night difference. For example, the temperature are different. And those issues cause severe load imbalance for global atmosphere modeling, especially when it goes to a large scale. So we carefully analyze this situation, and recently we proposed a new distribution strategy. So the numbers still refer to process ID. You can see now at every step, every process is in charge of 3 different areas, and it includes both ocean and land, north and south, and also day and night. So it will have a better load balance. After doing all those kind of redesign, we also try to develop tools like OpenMP, like tools, and also auto tuning tools, so that those kind of fine-grained optimizations can be easy to use for domain experts, for our users. And also for the earthquake simulation, our recent work, we have also performed very fine-grained tunings from thread level, from process levels, and also for the process level. In this picture, if you look at different colors, the orange refers to boundary condition, and the blue color refers to normal computations. So because the boundary conditions are different for different cube. So we design a non-uniform decomposition. We quantify those different cubes into 8 categories, and we try to make them equal to each other. So the overall load balance could be the same as possible to improve the performance. And we also scale those earthquake simulation into more than 39 million cores on our new systems. And this is the simulation result of our software. We managed to simulate 3 earthquakes. Actually, we can simulate any earthquake given the data. This is the Turkey, the Wenchuan, and also the Red Crest earthquakes. Also, in recently, we also studied some quantum computing because we have demand from partners from quantum areas. The key idea is to accelerate tensor network based on our systems. And those tensor networks can support very well for 2 types of quantum computers. One is based on quantum circuit, and the other one is based on photonic quantums. For both systems, we already have a quantum computer prototype in China, and their verification, some of their computation is done and analyzed based on our supercomputing systems. And that's some of the latest work on Sunway. In this talk, I also want to share some of our work on FPGA. Because if you are familiar with FPGA, you know that the hardware on the FPGA is programmable. So we can explore the performance potential by deploying a long pipeline of hardware cores. And the pipeline is kind of the same with the algorithm of the application, so that data can stream through those cores and get computed. For example, this is a 1.1-step implementation using FPGA to deploy a hardware pipeline for the 13.3 stencil. We first have a window buffer for accommodate all the 13 points, and then we have a stencil operator using the FPGAs. In our design, we also can, if we have more hardware resources on the FPGA, we can have a multi-step computations, and we can have a multi-point computation at the same time, so as to achieve a further level of parallelizations. And also for the molecular dynamics, we can use FPGA to deploy a hardware design to this CPU. One CPE in this picture is to process one cell computation of molecular dynamics, and we can have multiple CPEs within one FPGA to support the computation of cells for molecular dynamics. And also we find that the hardware level overlapping is possible, just like software level. For example, in this design, the stage 1 cannot be overlapped by stage 2 in one cell, but stage 1 can be overlapped by the stage 2 of another cell, so we'll achieve this kind of overlappings. And this picture shows the result that we have deployed the hardware support computing for different types of applications, covering all those 4 areas: shallow water, Euler equation, RTM from geophysics, molecular dynamics, and earthquake. The red number refer to the time to solution, compared with state of the art, compared with other processors like GPU, like CPU. And the green number refer to the energy to solution, compared with state of the art work. So for all those work, we can achieve both better performance and also lower power consumption by using FPGAs. And also now, we know that almost lots of processors have good support for AI computing. Some of them even deployed with AI unit. So we try to use this AI unit not only for AI computing, but also for numeric computing if we need them, because they are already there. if we don't use it, it could be a waste of resources. So we designed some methods to use those AI units. For example, they have a good support for mixed precisions. So we also have some work on mixed precision. In this work, we try to adjust the dimension of different variables. If two variables are different, have different dimensions, we try to use a dimensionless constant to make them close with each other so that we can have a better selection for reduced precisions. And then after the computations, we can reverse them to its original dimensions. And if we can implement this kind of algorithm, we can make the use of AI unit, because generally they will have a good support for lower precision. And if we are using FPGA, we can use hardware to deploy precision operators. And before the computing, and then after the computing, we convert it back to its original precisions. And also, those AI units have a very good support for matrix computation. So we try to, in numeric computation, try to find some more opportunity to use matrix. For example, this is an example we try to change finite differential computation into matrix multiplications by adding many zeros. And we need to find a trade-off so that the extra zeros can be overlapped by the performance improvement of the AI unit. For all those work, now we also try to develop software and tools so that those kind of low-level, fine-grained optimizations could not be easy to use and could be used by users from other areas. And also, we have some AI and quantum work for now. And those are all the publications I have mentioned. Some of the work were used, some of them were introduced in this work. If you are interested, you can you can contact me. Okay, I also want to take this opportunity to thank all my students, all the young talent students that were always there to help me. And also, our group is in charge of all being involved in several computing centers in China based on Tsinghua University. For example, we have the Wuxi Supercomputing Center that has the Sunway Tech Light, and we also have some computing centers in west area of China. And also in Shenzhen, we just established a new math plus computing centers. And also Professor Yutong Lu, she's in charge of the National Supercomputing Centers in Shenzhen. So because in the past decades, I was very lucky to have been invited to attend lots of international affairs, international events, which I really learned a lot. So I know the importance of international collaboration and try to make friends, just as Tolson mentioned in the beginning. So I want to invite all of you, if you are interested in those research and also in those computing centers, and maybe in those cities, you can invite us. We don't have, not only have, because those supercomputing centers covers a large area of China from east to west, from north to south. So they have different views, they have different cultures, and they have different food. So you're welcome to visit us in China, and we can enjoy all the collaborations, and also we can enjoy those views. Okay, so that's my talk today. Thank you so much.
For a second. Thank you again, and congratulations. Two announcements for you. First of all, be vigilant. Next year, at the beginning of 2026, there will be a call for nominations, and we all have the responsibility and the pleasure of nominating colleagues like Lynn for the Jack Dongarra Early Career Awards. So January 2026, all of us, one assignment, one homework. Look for your colleagues, early career, nominate them. Second, don't go away, because there is the top 500. We are very excited to listen to the top computers. And so with that, thank you for joining for this award ceremony, and enjoy the rest of the conference.